Hey everybody. So today I want to talk about two quick follow-up concepts that immediately, I should say, follow from our previous conversation about curvature. And specifically, once we have the definition of curvature under our belt, we can now discuss the oscillating circle and the evolute of a given parametrized curve. And we're going to start with the oscillating circle. So we're going to say as our sort of framework, let's take a parametrized curve, x. Let's let C be the locus of this parametrized curve, and let's look at a specific t0, so a specific moment in time on the parametrized curve. Then the oscillating circle to the locus C at the time t0 is going to be the circle of best fit at t0. And so when I say circle of best fit, what I specifically mean is that this circle will have contact order 2. Now, maybe just to quickly talk about, what do I mean when I say contact order? Bam. Right? Well, so contact order is more classically defined in terms of functions. And even if we haven't heard this language before, this is something that we're probably at least a little familiar with from Calc 1 and Calc 2. Right? So let's take a function, f of t. We'll make sure that it's defined at a given time t0. So here's my function f. This is going to be my time t0 right here. And so to give an example of contact order, I can talk about the line of best fit. That's our good friend, the tangent line. So that's going to be this point here. Here's our tangent line going in both directions. Right? And this tangent line, aka the line of best fit, will be the curve or a curve that has contact order 1 with the function f. Similarly, we can talk about the second degree Taylor polynomial, right? So this was the second degree function, or the quadratic function of best fit to our given function f of t, aka a parabola of best fit, and this will have contact order 2. So if I were to draw that here, right, that would probably look something like this. The parabola of best fit probably looks something like this, and that would be a curve of contact order 2 to the function f at the time t0. So more broadly, right, and we can sort of treat this as our more formal definition, more broadly, two functions will have contact order j if the following holds true. So our two functions f and g have contact order j if the functions agree at a given time t0, their first derivatives agree, their second derivatives agree, all the way up to their j derivatives. So two functions have contact order j if the functions agree at that point and the first j derivatives all agree at that point as well. All right, so we can see here how this line had contact order 1 because it's agreed with the function at time t0, and the first derivatives agreed with each other as well. Right? For our parabola of best fit, the first and second derivatives both agreed. In fact, that's how we originally defined, or how we helped influence our definition of Taylor polynomials. So when I say that the oscillating circle is the circle of best fit, it turns out that this will be a circle for which we have contact order 2. Now, okay, so we should really quickly clarify something here. The contact order, the definition of contact order that we gave below is between two functions, f and g. Well, here, we're trying to use it in a subtly different way, right? We're talking about the contact order between two sets in R2. Specifically, the contact order between a locus of a parametrized curve and a circle, right? This oscillating circle. And possibly neither of those might be functions in the traditional sense. So what do I mean by that? Well, let's take a look. If I move over here, right, let me quickly draw. Here is a parametrized curve in R2, right? And notice, even if I have sort of my x-axis drawn up here, I should say x-axis drawn down here, y-axis drawn up here. This is not a function in our typical Calc 1 understanding of a word function, right? Specifically, this fails the vertical line test. So really, in our pre-calc sense, this doesn't look like a function. And then we have our oscillating circle. Let me go ahead and draw that. Right, if I choose a point, and let's maybe choose this point right here, and maybe this is my oscillating circle there, right? The oscillating circle is also not a function. So neither of these are functions. What do I mean when I talk about the contact order between these two objects at this particular point in question? Well, what I mean is that we can focus in on this point and zoom in, and by restricting where we look, by restricting our domain or by restricting our viewpoint, we can imagine these as two functions, or it looks locally like two functions. Let's see what we mean here. So if I take this point specifically, let's take that to the center. Let's zoom in a little more. Oh, let's bring it back to the center. Here's our point again. And I'm just going to redraw this. Maybe here's just the piece of the circle that I want to focus on in a slightly darker blue. Right, so there's my circle. Maybe even that was too much. Let's try it one more time. Here is my circle, piece of the circle that I want to look at. And in a shade that's not quite black, but close to black, so to say here, right, here is my original curve. And if I focus on those two pieces, right, in this restricted domain, and I ignore the rest, so ignore the points of the circle and the points of the original parametrized curve where this failed to be a function, then in here, in this zone, these are two different functions, right? Again, I can draw my classic XY axis, right? By zooming in, these look like two functions, and if I were to write down those two functions, they would have contact order 2. So when I say that these two objects have contact order 2, that's really what I mean. By looking locally and writing it as a function, these two functions now would have contact order 2. So hopefully that clarifies that up. So because a parametrized curve and an oscillating circle will have contact order 2, that means that they'll agree locally up to second derivative. And a great sort of follow-up to that is the fact that that means the curve and the circle will actually have the same curvature measurement at the point in question. Right? In other words, so here is a parametrized curve x, and let's say this is the point x of t naught. Here's the corresponding oscillating circle. And what I really mean then is that the curvature of x of t naught and the curvature of the circle will be exactly the same. And of course, we saw last time that this can be written as kappa sub g of t naught. Right? So that will be our curvature in this case. This is great because this actually gives us a lot of information about the circle, right? The fact that we know this now means that we can actually completely determine where the circle is located in space, what its center is, and what its radius is, right? Because as a reminder, another great fact is that circles have this relationship between their curvature and their radius in that they're inversely proportional to each other, right? The radius of a circle is equal to 1 over the curvature. And equivalently, the curvature of a circle is equal to 1 over the radius. So in this case, right, the curvature of this circle is k sub g of t naught, I should say kappa g of t naught. That means that the radius of this circle will be 1 over kappa, right? And so if we want to record some facts about the circle, we can do that here. So we can say that the circle will have radius equal to 1 over kappa sub g of t naught. It turns out we also have enough information to figure out where the center of the circle is as well. So we can figure out where that center point is. Right? And so how do we do that? Well, we have to be a little clever. I'm actually going to find the center of the circle. Let me draw that right here. I'm going to find that point by thinking of it as a vector in R2 and doing vector addition, specifically by adding up the 2 points, or the 2 vectors. I'll draw this vector here, and then I'll add to that this vector here. And so that vector plus that vector will be enough to give us the center of the circle. Now, we have to figure out what those 2 vectors are, though. Right? The first vector is relatively straightforward. It is just pointing to the point on this curve x. So specifically, this vector is, whoa. Let's try that one more time. So specifically, this vector is x of t naught. Right? And so the center, we can find it by adding x of t naught and then plus the second vector. Right? And so to figure out what the second vector is, we have to think a little bit spatially, geometrically, about where this sits in space. Right? In particular, that vector is pointing directly into the center of this oscillating circle. So it's pointing perpendicular to the edge of the circle and perpendicular to this parametrized curve x. In other words, this pink arrow is pointing in the direction of our normal vector u. Remember, our normal vectors, our u's, were the vectors that pointed completely perpendicular to this curve and had unit length. And so if I get to this point, I'm going to have a little vector u of unit length pointing directly in the same direction as that pink arrow. Now, it might not be equal to the pink arrow. The pink arrow might be bigger or smaller. But how big is the pink arrow? Well, it's exactly the length of the radius of this circle. So it points in the direction of u, and it has length equal to the radius. In other words, if this little green vector is u, then the pink vector will simply be the radius of the circle, so 1 over kappa g times the vector u. And it turns out that's exactly the piece that we have to put in over here. So to get to the center, we take x of t naught plus 1 over kappa g of t naught times u of t naught. And so we've completely identified not only the radius, but also the center of this oscillating circle. And so the center of the circle actually has another name, which we'll introduce now. Circle. Right? And we can define this as the center of curvature for the given curve at the given point t naught. And that's summarized in this bullet point here. Right? If we have a parametrized curve, and if the curvature is non-zero, that lets us put it in the denominator. The center of curvature is the center of the oscillating circle, and it's given by that equation that we just derived. Now, the final thing that I want to mention is that this was true at a given point t naught, but this could be true at really any point t naught. So if I chose any given point, assuming the curvature is non-zero, I can calculate the oscillating curve at that point t naught. And if I take a whole bunch of different t naughts, a whole bunch of different points together, what I get is a whole set of points that I've calculated, and this will actually give me a new curve in the xy plane. Right? And if I take all of those centers of curvature together, right, and I look at just the locus of that set of points, what I get is what's called the evolute of the curve. And so it is given by this equation here, just the same equation for our centers of curvature, just taken at any given time t. So again, just to be crystal clear, right? If I start with a given parametrized curve x, at any given point, right? So let's say I look at this point here. At any given point, I can construct the center of curvature. Well, first the oscillating circle, and then find its center of curvature. I can do that for other circles as well. Right? Down here, it's a little less curvy, and so the radius of the oscillating circle is bigger. But if I do that for all of these different points, I get all of these different centers of curvature. Let's erase those circles. Right? And so if I calculate all of those points, and I calculate them every step of the way, what I'll get is a new curve connecting all of those, and that curve will be this evolute E of t. Right? And so the evolute is a curve that's created by x of t and is somehow linked to or related to x of t. And it's created by looking at these oscillating circles and their centers of curvature.